and I got to a 7-fold increase in the yield in 3 weeks.
It's quite compelling.
It felt good. It felt
Yeah.
really good. I did feel a bit smug. It has to be said. All of this data that just showed, look, it's really
works.
it's really powerful, guys.
Yeah,
It's
yeah.
really, like, honestly, I'm having fun here. Today, understanding complex living systems is hard, but does it have to be? I'm Markus. I'm a biologist.
I'm Phil. I'm a statistician. Together, we discuss the best experiments to cut through biological complexity. Join us to explore the shape of the next experiment.
Biology is this hugely complex, interconnected system. It's a product of evolution, and
Yep.
so that means that we have component parts which then come together in unexpected ways to make this emergent phenomenon that is any biological system we're looking at. And the issue is that the standard way that we're all taught to do science doesn't help us to deconvolute those interconnections. We hold everything constant except for the one thing we're looking at, and we see if that one thing's having an effect. But then what if that one thing actually has a different effect if something else is changing, right? So in this episode, we're going to be exploring the main thing that we're here to talk about, which is about multidimensional experimentation and how that can help to unpick those kind of complexities, which uniquely for biology are particularly prevalent.
Yeah.
So Phil, as someone who's been, teaching design of experiments, multidimensional methods for, more than 10 years at this point, what's your standard way of introducing to an audience, if you like, an expectant audience, about like the fundamentals of what multidimensional experimentation is all about?
Yeah, so because it's a slightly scary thing for some people, it's a little bit threatening. We're telling people that they've maybe been doing things wrong.
Right.
Yeah, I tend to start with a slightly silly story, a little sort of playful story. So it's a bit like a fairy tale.
Try and kind of like diffuse the sense of impending doom in the room. Kind of
Yeah,
thing.
a little bit. Yeah. So, bring people's defenses down in a nice kind of way.
Yeah.
So once upon a time, there were two scientists, Dr. Stevie and Dr. Charlie,
Okay.
and they're working at a life sciences company. And Dr. Stevie is a very experienced senior principal scientist, level
grey hairs.
3. Yes. And Dr. Charlie was a young graduate scientist. And one day, their VP of R&D came to them both and said, "You've got 9 attempts to optimize this process.
Okay.
And you're only allowed to change pH and temperature.
Okay.
And whoever gets me the optimum yield wins this competition."
Okay.
Right? So you've got 9 attempts, 9 trials of this process, changing pH and temperature. So you can change pH between 6 and 8,
Okay.
temperature between 30 and 70.
Okay.
So I asked people, think about what you would do in that situation. Now, Dr. Stevie, being the experienced scientist here, I know exactly what I'm going to do.
Okay.
I've been doing this for years. I'll do it the good old way. Dr. Charlie, on the other hand, inexperienced scientist. I'm really not sure. This sounds complicated. I don't know what I'm going to do. I think I'm probably going to lose this competition. But just then, she was scrolling through her LinkedIn feed,
Okay.
and she came across this strange old man saying, well, what you should do when you've got multiple factors is to thoroughly explore the possibility space
Is
by
this in a
changing.
particular strange old man? Phil?
Could be, I mean, it might have a hashtag DOE by Phil K.
Yeah,
possibly
something
in there.
along those lines. Yeah.
So the two scientists went away and did their experiments. 2 weeks later, came time to present the results to the VP of R&D. And I've got Dr. Stevie's results here. So Dr. Stevie went first, obviously being the more experienced scientist, and laid out the results in a nice Excel sheet with nice coloured conditional formatting.
Okay.
The VP of R&D was delighted. And the VP of R&D also liked the fact that what Dr. Stevie had done was to use the tried and tested method of one factor at a time.
Okay.
So for the first 5 trials,
Yep.
Dr. Stevie had set a pH at 6.5 So it doesn't change for the first 5 trials.
Okay.
But temperature has changed 30, 40, 50, 60, 70.
Logical.
So from those first 5 trials, Dr. Stevie deduced that the optimum temperature was 60 degrees, giving a yield of 55%.
Right.
So then, having found the optimum temperature, Dr. Stevie fixes on that optimum temperature of 60 degrees.
Right.
All seems quite logical, right?
Perfect.
And so he then varied pH for the final 4 trials, 6, 7, 7.5, 8.
Yep.
And ultimately found pH of 7, temperature of 60 gives a yield of 57%.
Yep.
And at this point, Dr. Stevie's thinking, might as well just walk away. I've definitely won this.
Yeah, slam dunk.
So then comes the time for Dr. Charlie to present her results to the VP of R&D. And the VP of R&D was shocked because it didn't seem like there was any structure to the way that Dr. Charlie had varied pH. So it was like pH 6, then 8, then 7, then 7.5.
Right.
She hadn't fixed one factor at a time.
Yeah.
She wasn't, changing just one factor at a time. It just seemed like it was all random.
Right.
But then the VP of R&D noticed that one of the trials had given a yield of 88%.
Right.
Which is massively
Somehow
higher.
she'd got lucky.
Well, exactly, yeah. Yeah, she'd just tried things randomly.
Yeah.
So at this point, Dr. Charlie presented the results in a slightly different way.
Right.
So she plotted the 2 factors that had been varied.
Right.
So pH and temperature.
Right.
So we've got pH on the y-axis and temperature on the x-axis.
Okay.
And what became apparent then was that these 9 trials formed this beautiful matrix, this
not so
beautiful
random.
3x3 matrix.
Yep.
So what Dr. Charlie had done was to thoroughly explore all of that possibility space in the most efficient, most effective way, just covering all the possibilities. Whereas when you plotted Dr. Stevie's results in the same way, because he'd just changed one factor at a time, it looks really weird.
You've essentially just got like 2 cross sections through that 2-dimensional space.
Yeah.
And so then that makes it obvious that actually you're dealing with a 2-dimensional space, right?
Right.
Like when you plot it that way.
Yeah.
Right.
Yeah. And there's these big gaps around the sides, around the corners of this that just haven't been tested, which that would be fine if these things just behave uniformly and you can just sort of interpolate between.
Right.
But, as Dr. Charlie had found, actually, there's quite a weird behaviour here. One of the corners, there's something very different happening. You've got much higher yields in that corner.
Yeah. So in this toy example, we've got the optimum temperature depended on which pH it was set at. Right?
Precisely.
And so the 2 are interconnected.
Yes.
Right.
And so that was a really efficient way of exploring that. Dr. Charlie wins the competition, is promoted to Director of Innovation.
Right.
Dr. Stevie's punished by being made to work in IT. And, so it's a silly story.
So you make sure that there's nobody from IT in the room when you're describing this, right?
Yeah, hopefully no.
I mean, I think that it is a silly story and it's meant to be, obviously, but I think it brings out a few things. And I just actually took a note as you're writing it, which it brings out something that's quite important. And maybe when we're thinking about the adoption of these kind of multidimensional methods, because like you say, the VP was quite pleased with the OFAT method, right, with the 1 factor at a time method. And, nobody ever gets penalized for just doing things as they've always been done, like that kind of tried and tested. And I think this is particularly within biology, we're not, that people aren't measured necessarily by the outcome. They're measured by the effort, because biology can always kick you, remember, right? So it's if a biological experiment goes wrong, then that's the natural order of things a lot of the time. And so there isn't really much of a pressure to sort of say, oh, well, is there a more powerful way we could be kind of exploring this space? And I think that's part of that cultural thing of like, then maybe not, adopting a more multifactorial method. And, I think there are lots of different things, though, that because it is fundamentally a different way, not just about doing science, but the way you're thinking about science. Yeah. Right? It's a genuine paradigm shift, right? Yeah. And that takes a big leap. And in my own experience, both as I adopted these methods myself longer ago than I'd care to remember at this point, but also as I see other people going on that journey of like going, you know, and thinking about these things, you sort of see that there are various hang-ups along the way, you know, kind of, I mean, you obviously for the sake of introducing the idea, you use a very simple system.
Yeah,
right?
just two factors.
Like two factors. And you can kind of think, oh, right, well, you know, nine runs. Yeah, that kind of makes sense.
Yeah.
But then, you know, we're talking about doing, you know, especially with the complexities of biology, like what about 15 factors or more, right?
Yeah.
And so then you kind of start thinking the immediate thing is, but hang on, doing all the combinations of all of those factors, you know, that can't be possible. That's like the first thing that you kind of run into as the first objection of many.
Yeah.
Right?
So that's something you have to get to. I mean, I think before we even get to that, we have to kind of get over some of the language. So we're talking about factors here, and you know, people listening, watching might not actually know that what we're talking about there is the input variables, the things that you can change, that you can control. Yeah. And then we're interested in the effect of those on the outcomes, which we generally call responses in this situation. Yeah. And you know, the trials we would call runs within one experiment. So there's all this language that I don't think helps. I think that's one of
so
the
much
barriers.
jargon. Yeah. You know? And DOE does, like, just like a lot of different disciplines, it has its own way of talking about things. Like, you know, more classically, factors would usually be called parameters, I think. But in DOE, for some reason, we call them factors. Yeah. And then, like you say, there's the things we measure as responses and so on. Yeah, I mean, I guess we'll try and make sure that we don't use too much jargon as we go and keep it as accessible as possible.
Yeah, we're already into you know, going between design of experiments, DOE, and multidimensional experiments and multi-factor experiments. Yeah. You know, we mean the same thing by all of those, but, you know, again, there's the language of that, I think, is not helpful.
No, it isn't. It isn't. And design of experiments in particular is not a particularly helpful term. You know, everyone designs their experiments. You know, an OFAT experiment is still a design. But like what we're talking specifically here is obviously about multidimensional. Yeah. And the importance for biology. And, you know, like, I mean, as we were sort of saying, like, in any given biological system. So first time I ever used DOE, I wasn't that far away from Charlie in your story in a lot of ways. So I was relatively fresh out of my PhD and working in a job where I had to optimize a system for producing a particular fragrance compound, as it turns out. And you know, I was keen. Yeah. You know, I was a new scientist, and I wanted to show that I was doing this stuff rigorously. And I started writing down all of the factors, all of the parameters that might affect the system. And I pretty easily got to 40. Wow. You know, I mean, and it's not hard in a biological system to get to 40 factors or more. And, you know, I tend to tell people if they're not getting up to that kind of level, they're not really trying hard enough. You know, it's like there are so many things that can affect a biological system. And then I realized I had 4 months to do this optimization. So it's kind of a time constraint that I was most worried about. Because if you were to do that one factor at a time and you did one factor per week, you know, you're gonna run out of weeks pretty quickly. And that time was meant to include then scaling it up in you know, fermenters in stirred tank bioreactors as well. And the thing that I haven't really spoken about so far is that actually this was 7 years after I'd first heard about design of experiments, about multidimensional methods, and I'd kind of been ignoring it all that time. And I hate to admit it, but I think maybe one of the reasons I've been ignoring it is because it was my dad telling me that I should be using it. And, you know, he's my dad, so what does he know, right? So, yeah, you know, like 7 years after he'd first sort of brought these things up with me and I'd had all these objections and I'd never used it, I was then faced with a system where it was plainly obvious that I needed to be looking at more than one factor at a time. And it wasn't because I was thinking about how factors interact with each other. I wasn't thinking about these unexpected corners where, you know, you might have a much higher yield. I was just thinking, I've got all these factors, I've got to get through them somehow. But yeah, then immediately you have all these kind of hang-ups of like, oh, you know, I've got 40 factors.
Yeah, that's overwhelming.
I want to be, you know, doing a decent chunk of them. And, you know, obviously you're going to prioritize the ones that are most important. But I got down to 11 factors. Right. Okay. And so if you were then thinking about, okay, even if we strip it down as much as we're only going to look at each of those factors at 2 different settings, at two different levels, there's another DOE jargon, at two different levels, then the number of design points you have, if you want to look at every combination of two levels for 11 factors, is 2 to the power 11, which I think it's around 2,000 actually. It's like the way that so there's 2,000 potential runs that you could run to explore that system, even just at two levels. And that's immediately like, well, I mean, obviously there's no way you can do that. But then what DOE tells you is you can then strip that down, right? And you don't have to do 2,000 runs. You can do, and in that case, I did 32 runs. Right. So 2 orders of magnitude difference. And this is something which I just feel like, and whenever I'm giving talks about DOE, like you can see that people struggle with it. Right? And you have to somehow explain to them that actually, don't worry. Our intuition about this isn't necessarily what's correct.
Well, I mean, when I'm presenting it, I often talk about that being the magic of DOE, of multidimensional experiments. I sort of wave it away as, don't worry, that's for the statisticians like me to worry about how we can do that, But I also, more seriously say, it's not really magic. It's a science in itself. Statistics is a science, and it's a science about how you make the best use of data to understand, whatever the system or process is that you're interested in. But that is I agree. How do you go from, we've got this 11 dimensional system, with all these thousands of possibilities, even if we're just looking at low and high settings of each factor. How can I possibly understand all of that in just 32 runs, 32 trials?
Well, and it gets even worse, because with the complexity of biology at Synthase, what we did in the early years of Synthase is we were really trying to push the envelope of what was possible. And so we pushed it up, like the biggest one we did was 27 factors.
I mean, that is incredible. There aren't a lot of examples out there where people have really done that.
We were quite proud of ourselves. It was a guy called Vishal Sanchania, and he was almost like a machine doing these experiments. But there's no way that he did whatever it is, the 32 million experimental runs. He actually stripped it down to 256. Again, using the magic principles of DOE, right? Like it was quite a sight to behold, because he then had to do such meticulous planning to, like, because you've got 256 runs where every single run is varying over 27 factors and no run is replicated, right? So it's all different.
Wow.
But like, you can work out sort of coping strategies for it, and it was a particularly memorable moment where walked in the lab and I saw him dual wielding like 2 multi-channel pipettes, setting up these plates. And he'd done this very clever thing of like taking the pipette tips out in the pattern so that like wherever it was missing, he could pick up all the tips that were remaining, and those are the additions he had to make for that particular factor at that particular time. Anyway, suffice to say, it was hugely complex to do. But he could do this 256 run experiment to explore 27 factors simultaneously. And when I'm exploring about why that might be the case and why we just don't get it as humans, I kind of think that actually our minds just aren't really that well set up for thinking about things in high dimensions. We walk around a world of 3 dimensions, and going much beyond that, just like we don't have any kind of naturally wired heuristics in our brain which can just help us think about that. And so what might seem incredibly counterintuitive might in actual fact be completely fine when you're getting into these high dimensions. And the other thing I tend to say to biologists to try and reassure them is like, okay, let's just think for a second about, we do a 11 factor design and 32 runs. Well, that means that actually for each of those things that we're investigating, you're comparing 16 runs with 16 runs. And it's a bit of an oversimplification, but like you do have 16 runs at that level and 16 runs at that level. And then you ask, how often do you replicate 16 times? Right. So actually, in one way, we've got very few runs looking at things, but in another way, it's actually really powerful.
I mean, literally powerful, statistically powerful.
Okay, more jargon. That's a niche statistics joke, but it's literally more powerful. in its ability to distinguish signal from noise.
Yeah.
And so like that's a big hang up. And the hang up that caught me for the longest is, we've just been talking about 2-level designs, right? And so, I already knew, my maths is relatively limited, but I knew in my kind of arrogant way when my dad was telling me about this, but all you can model is a straight line with 2 factors.
Right.
With 2 levels, sorry.
Yeah.
And biology doesn't move in straight lines. It's famous for not moving in straight lines. It's very unpredictable, very complex. And so I just I didn't even wait for the explanation. I just kind of like, oh yeah, this doesn't apply to what I'm doing.
Yeah.
I can imagine it might be useful for whatever you did, Dad, who was also a biologist.
In the steam age.
Right? Yeah, exactly. Yeah. But like, it's just that kind of dismissive arrogance of youth, isn't it? Like it was this kind of hang up of just 2 levels doesn't make sense. And then it's only when you look into it more, it's like, well, of course, you're not only going to look at those 2 levels, but you do many sequential experiments, where you then use these iteratively to explore a much more complex space. And then it makes sense.
Yeah.
But yeah, without that, then you can end up really hung up on these things, especially, as we've discussed, that, this is a way of changing the way we're looking to do science. So
yeah.
Obviously, like, subconsciously, you're almost looking for the things which are just like, oh no, my way of doing things is fine.
Yeah.
And, I think, you could pretty much look at anybody who's gone on that particular journey, particularly biologists, I think, and we've all got these kind of stories of, oh yeah, and then I realized maybe I should try it. And I think for me, like that's always like, whenever I'm giving a first talk, I'm not necessarily thinking about like convincing people all the way.
Yeah.
In that first talk, it's more about like, oh, there might be something interesting here. Like I should look into this more, and then I feel like I've done my job.
Yeah. 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 I mean, like you say, it's not intuitive. I mean, statistics isn't intuitive. I don't think, I don't know if you've read Thinking Fast and Slow.
Yes.
By Daniel Kahneman.
Yeah, classic.
So, a lot of that book is essentially about how humans just don't think rationally a lot of the time, and they're not good at thinking statistically. Even statisticians often don't do a good job of, thinking statistically and kind of coming up with statistically properly powered experiments and things like that. So, there is just that massive gap between our human intuition and the way that we can better do experiments through these high dimensional techniques. I mean, I think some of it just comes down to, well, it works. Look, here's a silly story about where it works, and here's a story from Markus and Vish about how it works in biology.
Right. And I think like this is the other component that you always have to have, right? And I think both of us are used to actually doing these explanations where we get to have slides of data and things, which make it a lot easier. So, in this format, we'll have to think a little bit more about how we can convey it just with words and with hand waving. But like, that first time I used DOE, and the reason that I've become the kind of zealot that I now am about it, like, just ridiculously evangelical, is because, you kind of take a load of stuff on faith, you take a deep breath, you plunge in, and then that first experiment that I ran, and it was 32 shake flasks back then, where, so you've got these things of this kind of size. And you're, like with maybe 50 or 100 mils in there, in each one of them. And they were varying over 11 factors. So I literally had them all arrayed on a bench, and then I'd organize them according to whether, which factor I was doing, and I'd split them in half, and I'd do the low level in one lot and the high level in another lot. And so it was a hell of a lot of work, really, really hard. It would take me a good week to plan and then actually run the experiment and then analyze them afterwards. But unlike my experience of biology up to that point, which was you can easily put in a week. I mean, in my PhD, I had protocols where I'd be working for multiple weeks at a time, often in a cold room. And then, it'll go wrong again. And I was like, oh, it's gone wrong again. And that was my normal sense of the progress that you can make in biology. And from the very first multidimensional experiment I did, I made definitive progress. And not only that, but I could see why. I could see which of the factors I was investigating were having the effect that I was looking to have. And it felt exhilarating. It felt really, really cool. It's like, oh, wow, I'm new in this job and I've just done an experiment. I went out on a limb. I took a deep breath and I plunged in and I went for it, invested a lot of time and energy into doing it. And it's given me like this insight and a yield increase.
Yeah.
And then the subsequent 2 experiments, because I did 3 experiments in total for that campaign, and I got to a 7-fold increase in the yield in 3 weeks.
It's quite compelling.
It felt good. It felt really good. I did feel a bit smug. It has to be said. Tried to, kind of contain the smugness, and I tried to then, talk about it with the rest of the company. And it was interesting even then, like they had all of this data that just showed, look, it's really powerful, guys. It's really, like, honestly, I'm having fun here.
Right.
Like it's really cool. And I actually spent a couple of weeks crafting like the perfect PowerPoint, right? To like, talk about the principle of DOE and how I was doing it. And then here were my results, and got to this 7-fold increase in yield in 3 weeks. And I just thought, of course, everybody's going to want to use this as well.
Interesting.
And not only did they not pick it up, except for there was another younger guy in the team who was also quite keen, and actually the leadership were really keen. Like they knew about DOE and they were keen for the company to use it more. But like everyone else, like kind of the more established, the Stevies of your story, right? I found I had to try and reconvince, even when I wanted to do it again. It was my experiments and my time, and it's just like, oh, but can't you just get that done in a quicker experiment?
Right. Yeah.
Why do you have to use this DOE for everything now? Like surely this one you don't need to use it for. And it's like there is a real resistance.
Yeah, I can remember it being within the company that I worked with before I joined Jump. There were real supporters, real champions of DOE, in the management, but there were cases where they would default to that comfort zone of, well, actually this is a case where design of experiments isn't going to work. And it was really interesting to me. I think when the pressure was really on, and when it's like, we have got no chance of understanding this without doing a really smart experiment, it was almost like that was more likely, okay, we'll go back to the comfort zone of one factor at a time. We really don't want to take any risks here.
Right.
We don't want to be...
Even though you're taking a dramatically bigger risk by going OFAT, right?
Yeah. There was literally no chance of understanding, just by doing a one factor at a time approach. So
that's often a question that I get actually, when we've done things. It's like, okay, what does DOE not work for? Right. It's almost like people are like, oh, you're snake oil salesman here. You're claiming that you can cure anything with this one, magical potion kind of thing. I never dare to call it magic because I'm so aware of that kind of pushback. And people often want to be like, oh, where will it not work? And so I've tried to think of spaces where it does work and where it doesn't. Where I think where it's most powerful is where you have some kind of a landscape that you're exploring, which has, some kind of smoothness to it, I guess. Right. So, you do your first experiment here and it points in a particular direction. And so then you can move up the space and you make very rapid progress exceptionally quickly, 7-fold yield increase in 3 weeks.
Yeah.
And that's why it's working so well. But I think, biology also has these areas which don't necessarily fall so neatly within that kind of like smooth space.
Yeah.
Particularly if you're thinking about like genetics. Genetics is a string of A's, T's, G's, and C's. It's an exceptionally discrete space. There isn't something that's halfway between A and a T. And similarly, like you change one of them, and a protein can go from functional to non-functional.
Wow.
Right. It's an incredibly kind of complex space, and so that's a space which instinctively I would have thought, oh, right, that's where DOE wouldn't be so powerful in its classical form, right? Because it relies on those relationships.
There's not many stories of using it in that kind of a
maybe this is something we can dive into a bit more, because there are some stories which are really exciting, and there are companies that do this. But I think there are, at least like pointing out that there are spaces where DOE would have more difficulty, then that, it shows that, we're still humble in the face of that complexity, right?
Yeah.
We just have found a tool that's more powerful,
Yeah.
right? But I think there are some biological systems where things are more tough, right? And I think where, the classic way that you might try and explore those spaces, like systematically, would still need a lot more runs, right? So we've spoken about like those instances where you can strip it right down, like from millions of runs to 256 runs, or the first time I used it, going from 2000 to 32. But there are some places where biology is still this hugely complex system, and you need more runs to work with it. And so what would be interesting to explore in the next episode will be like the changes that are happening in biology to do with automation, which now allow us to do a lot more runs.
Yeah, it's very exciting stuff.
But I think for this episode, we can probably leave it there.
Yeah.
And we'll talk again next time.
All right. Cheers.